Hello viewers. So we have a question under acids and bases. It's saying define the following acids and give examples. Also show how ionization occurs until all protons are released. The first one is monoprotic acid. The second is diprotic. The third is triprotic. And the fourth is tetraprotic. So we need to define, we need to give one or two examples, and then we need to show the ionization until all protons are released. So let's do that. Let's get one after another and see how we can define, what examples we can give, and also show ionization. So the definition is a general one. When you look at this part here, this part here, I've shown to say we have 1, 2, 3, 4. So we'll be picking one there, the definition. And then on this part here, we have it, then we have them. So we'll be picking which one is suitable according to just English. Yes. So let's quickly start from the monoprotic acid. Now, what is a monoprotic acid? A monoprotic acid is an acid that contains one. So we are picking just one here inside brackets. Ionizable hydrogens atoms per molecule and can donate it. Since it's one, we're picking it as a proton in aqueous solution. So we're not using as protons, but we are saying as a proton in aqueous solution so that our English is correct like that. So that's how you define a monoprotic acid. Just an acid that contains one ionizable hydrogen atom per molecule and can donate it as a proton in aqueous solution. Well, so we are done with the definition. Let's give examples. What examples can we give for monoprotic acid? I'll give you two examples. The acids. So here we are going to have the first one. The first one is hydrochloric acid. So hydrochloric acid, in the first example, it has got a formula, chemical formula that looks like this, HCl. So that's hydrochloric acid. And the second one I'll give you is, the second one we'll have is nitric acid. Nitric acid has a chemical formula that is HNO3. So those are the two examples we're going to give under monoprotic acid. Then we'll show the ionization. Now, this type of acids contain only one acidic hydrogen. We can see from what we have here, this has got only one acidic hydrogen, and this one has got also one acidic hydrogen. So this is the only hydrogen these acids can donate. So their ionization just contain one step or involves one step. To ionize is to basically convert into ions. So to write the ionization equation, we need to put the acid in water and then we see what it produces on the other side. So let's show the ionization here. So hydrochloric acid, put in water. This one will give us on the other side, we're going to have the hydronium ions, H3O plus, and we're going to have a Cl minus on the other side. So this is the ionization of hydrochloric acid. It's a strong acid, so it uses just a single arrow because it ionizes completely. So this is the ionization we have. Now look at how the charges are changing. Here water didn't have any charge, so we'll say it had 0 charges. It has 0 charges. Even the acid here has a neutral charge, which is 0. What happens here is when you give a hydrogen, you are losing, you are subtracting. Let's say you are subtracting by 1. So you are losing. When you give a hydrogen, you are losing. So if your charge was 0, when you say 0 minus 1, this will basically give you minus 1. This is the reason why the chlorine that remains here after giving out a hydrogen has a negative on the other side. Receiving a hydrogen or gaining a hydrogen is gaining a plus 1. So you can see the water here basically received the hydrogen. So when it receives a hydrogen, the charge was 0. 0 plus 1 will give us a plus 1. That's why you can see we have a positive charge on that side there. It's because of the receiving of the hydrogen. Hydrogen as a proton is basically protons are positively charged. So yeah, that's what is happening there. In terms of how we come up with what is going to be found on the other side, it's very simple. What is happening there is when you put an acid in water, an acid is defined as a proton donor according to Bronsted-Lowry theory. So it's defined as a proton donor. In other words, it donates a proton to other substances. So this acid we have here, hydrochloric acid, will donate its proton to the water that it is reacting with. So it will give its hydrogen to water here, and then when it gives the hydrogen to water here, the hydrogens we have for water are 2. When it receives 1, it's going to produce the hydronium ion here, where we have 3 hydrogens, the oxygen, and a positive charge. So a plus charge, I've explained that already, how we are getting into that. So this is how we are receiving or having this product here. Then whatever remains when you give out a hydrogen, you write it on the other side. After giving out this hydrogen here, what remained was just chlorine, and that's what we've written on the other side. Don't forget the charge. When it gives, it means it's going to subtract by 1. So if the charge was 0, minus 1, that's minus 1. So we'll see how other changes in terms of charges will come out from types of acids. So for nitric acid, the same applies. We're going to have HNO3 being put in water like this. And on the other side, we're going to have H3O plus. And then what remains on the other side when we give a hydrogen is NO3, and it will get a minus charge. So this is what we have. Now the second one is diprotic acid. So diprotic acid, according to the definition again, we are going to, di means 2, mono means 1, that's why we picked 1 from the bracket there. Mono means 1, di means 2. So in our definition here, we're going to say the definition of a diprotic acid is that an acid that contains 2, or it is an acid that contains 2 ionizable hydrogen atoms per molecule and can donate them. Now we are using them. It was just for monoprotic, the rest will be using them. So it is an acid that contains 2 ionizable hydrogens per molecule, hydrogen atoms per molecule, and can donate them as protons in aqueous solution. So we'll go on and give examples. What examples do we have here for diprotic acids? So for diprotic acids, the common example that we can use here is sulfuric acid. Let me start by writing the name. So the first one we are using here is sulfuric acid. Sulfuric acid, and this sulfuric acid has got a formula of H₂SO₄. Then the second one we're going to use here is carbonic acid. Carbonic acid has got a formula which is again H₂SiO₄. So those are the two examples we are going to use. The two examples we are going to use. On the ionization, remember these are now diprotic acids. They contain two hydrogens that they can give out. You can see we have two hydrogens here, we have two hydrogens there. So they can give out two hydrogens. Now, let's go to the ionization steps. Since they can give out two hydrogens, they will have two ionization steps. So let's go into that. We'll use just one acid, then you can apply the same concept on the other. So we have H₂SO₄. We are putting this in water. And when we put this one in water, now sulfuric acid again is a strong acid, so it will use a single arrow. So we have sulfuric acid put in water. On the other side, we're going to produce the H₃PO+ ions. Then this will be added to what remains there when we give one hydrogen. We're going to remain with the hydrogen that is connected to SO₄. And the charge here will be a minus. The charge there will be a minus. Yes, so we'll have a minus charge there. This is the first one. Then the second one, remember on the product here, we still have a hydrogen. So we want to show the ionization until all the hydrogens are used. So we're going to get this part here and put it in water again. So we're going to have HSO₄ minus. We are putting that in water. And when we put it in water, what we are going to produce on the other side, we are still producing hydronium ions. And those are positive charged ions. And what remains here now, when we give one hydrogen, the remaining hydrogen will only have SO₄. The charge will now be 2 minus. The reason why is, as we earlier discussed, when you lose a hydrogen, you are gaining a -1. When you lose a hydrogen, it's more like you are subtracted by 1, meaning you are gaining a -1. So if your charge was already a -1 added to -1, what you have here is -1 -1, and this will give you -2. So our charge there will end up being a 2 minus. So that's how we come up with the charges. So that's what we have for this one. We have given two examples and we have given the two steps. So you can apply the same concept to carbonic acid, just like we did to this one. We'll go to the next one. Let me just get rid of this part again. Okay. All right, so the next one is triprotic acid. For tri is a prefix that means 3. So again, our definition will be an acid that contains 3. We are using 3 now. Ionizable hydrogen atoms per molecule and can donate them as protons in aqueous solution. Yes, so that's how we define a triprotic acid. All right. So now let's give examples. What examples do we have for triprotic acid? The first one, which is the common example, is phosphoric acid. So start by writing the names and then the formula here. So this one contains 3 hydrogen and it looks like that. Now its charge is that. Yes, so we have that H₃PO₄. And then the second one we're going to use is arsenic acid. So we have arsenic acid. And arsenic acid looks like this: H3 AS for arsenic, and then so these are the two examples we're going to give for a triprotic acid. On the other side, since we have 3 hydrogens, it means our ionization steps until all the hydrogens are used will be 3 as well. So let's start with the first one. So the first step, we're putting it in water. We'll have H3PO₄ being put in water like that. Then on the other side, to show that what we are going to have on the other side is the hydronium ions as usual. And then what remains after giving a hydrogen there is H₂PO₄. The charge becomes a negative there. Charge becomes a negative. Then the second step will be getting the product there, which is H2. Look at that. It's H₂PO₄ minus. We are putting it back in water, and we are saying after doing that, what we are going to produce on the other side is we'll have H3O plus, and then this will be added to. When we give a hydrogen again, what will remain is H₃PO₄, like that. So that's what we have there. The charge, it was -1, now it's going to be -2. Then the last one will be now us putting the product again back in water. The charge is 2-, and this will be added in water to produce again. On the other side, we still have the hydronium ions added to the PO₄. The charge now becomes a 3-. So this is what we have as the steps for a triprotic acid, like that. Given examples, the definition and ionization steps. So let's go to the last one, which is a tetra. All right. So for tetra, you know the drill now. We're just picking, tetra means 4. So we are picking 4 there. So it is an acid that contains 4 ionizable hydrogen atoms per molecule and can donate them as protons in aqueous solution. The 2 examples we're going to give here is, so we have the first one, which is the silicic acid. So this one has got a chemical formula which is H4. It has 4 hydrogens. Then we have silicon connected to oxygen, 4 atoms of oxygen. Then the second one that we have here is phosphoric acid. So that's what we have, and this has a chemical formula. Now to save space on my ionization part, let me write the chemical formula down here. This is H4, P2, and we have O6. So it looks like this. This is hypophosphoric acid. So those are the 2 examples we're going to use here. There's two examples. To show the ionization, since they contain 4 hydrogens, it means we're going to have 4 steps again. So we'll do those steps. Let's start with the first one. We're just putting, we'll use just one again. The H₄SiO₄, we are putting it in water. And this will give us on the other side, we're going to have hydronium ions as usual. These are positively charged ions. Then what remains there will be H₃SiO₄, like that, with a negative charge. The second step, we're going to put the product in water, which is H₃SiO₄. Put it back in water, and what we are going to have again as 2 hydronium ions, and the only positive charged ions, and then we'll have H₂SiO₄. The charge now will be a 2 minus. The charge now will be a 2 minus. 2 minus there. Then the third step is we're putting H₃SiO₄, then added in water. This will give us on the other side still the hydronium ions that will be added to what remains there. Now we'll have H₃SiO₄. The charge is now a 3 minus. Then the last step, which is the fourth one, will be we are putting the H₃SiO₄. Don't forget the charges. We didn't put the charges on the second step here, and we didn't put the charge on the third step here. Is a 2 minus, and the last one here we have a 3 minus. Then we add it in water, and this will basically give us again the hydronium ions that are added to SiO₄. All the hydrogens are used, so we don't have any now, and the charge will be a 4 minus. So these are the 4 steps that a tetraprotic acid will go through. Yes, so we've defined each of these, and we've given their examples, and we've also given their ionization steps, like that. So before I end the video, let me show you how you can use a general acid, the general acid representation, to basically show the steps for each. So let's do that. Without using actual acids, we can still show the ionization of each of these. By doing this, for a monoprotic, we are going to say the general one will be HA. This is the general representation for an acid. So we're going to have HA, and we are putting it in water. The A is the one connected to the hydrogen, the conjugate connected to the hydrogen. So we'll say the substance connected to the hydrogen. The hydrogen is the acidic hydrogen that makes it an acid. So we'll put it in water, and it will, on the other side, using the double, considering it to be a reversible chemical reaction, we'll say we're putting this one in water, and what will produce on the other side is basically this acid here is going to give a hydrogen there, will still produce the hydronium ions, which are basically positively charged ions, and this will be added to A minus. So this shows the monoprotic ionization of an acid. You can show it in a short form again. The simple dissociation doesn't include water. we don't show water. So the HA will just convert on the other side. And the hydronium ions, which are H3O plus, are represented by just H plus. So H plus ions are the same as the H3O plus ions. They represent the same. Then this will be added to A minus. So this is the simple dissociation equation, and this is a full dissociation, a full representation of the dissociation. And this is the simple representation of dissociation. So this is for a monoprotic acid. Let's do it for a triprotic acid. No, diprotic first before you go to tri. So here we're going to have di, it means it has two. So we'll say we have H₂A. And when we put this one in water, on the other side, we're going to produce steel. In this case, we are using everything. We are writing the full dissociation. So it will be H3O plus added to what remains there. What will remain there will be now HA minus. And then when we put the second one, that remains there in water. So this is our first step. This is our second step for a diprotic. When you put this one in water, what we are going to produce again will be the hydronium ions still that are added to. Now what remains there will be A, but this A will be having a charge of 2 minus. So without using an actual acid, you can basically show the ionization steps. Yes. So for a simple dissociation, again, this can just be like this. You're putting H₂A in water, and you don't show the water. On the other side, you're just going to have a representation in form of H plus, and then this is going to give us on the other side was to have HA minus. Then when you put HA minus here again, you're not showing water. You still produce the H plus, and what remains here now is just A2 minus. So that's how you can show the simple dissociation. So you can do the same to triprotic and tetraprotic. What you are going to be doing is you'll just be increasing the number of hydrogens here. So for tri, there will be 3. For tetra, there will be 4. The last part that I want to cover in this video is the use of state symbols. Now, we didn't use the state symbols, but we should always use them as we write our dissociation equations. State symbols are symbols that show the state of matter. Is it in liquid form? Is it in solid form? Is it in aqueous form? Or is it in gaseous form? So for the acid dissociations, we basically use aqueous and liquid for water. So what I want you to do is, in all those dissociation equations that we're writing, put each acid on the reactant side here. Let's get one example of the acids we had. So let's say we have hydrochloric acid that we're putting in water. This one is giving us H3O plus, and then we have Cl minus. Now in each of those dissociation equations we're writing, the acid, put the acid in aqueous state, put the water in liquid state, and put the hydronium ions in aqueous state, and also the conjugate in aqueous state. So in other words, the 3 parts will be in the states of aqueous, and then just put water in liquid state. So as you write those dissociation equations, please make sure you're putting the state symbols. We didn't do it, but do it since we've explained it at the end here. So always use the state symbols as you are writing the dissociation equations. The other part is the use of arrows. So you need to understand the type of acid that you are dealing with. Is it a strong acid or is it a weak acid? If a strong acid, the arrow you need is a single arrow. Strong acids completely dissociate. So we use a single arrow for strong acids. If it's a weak acid, you need to use two arrows because they partially dissociate. So we use two arrows, say they will go this side and they can come back on the other side. So yeah, use two arrows for for weak acids and use a single arrow for strong acid. How do you know that this is a weak acid and this is a strong acid? We basically have 7 strong acids that we use as reference. So if you see that the acid you're dealing with is not among those 7 strong acids, it implies to say you are dealing with a weak acid. So all you have to do is know the 7 strong acids, and whatever is out of that list, you consider it to be a weak acid. So this is it for this video. Kindly subscribe to our channel and comment